就比如你把水。Thank you. Yeah. Okay, so morning everybody. Sorry about the mess here. For some reason, you love technology until you discover that sometimes lets you down. And well, okay. So we're live now. Let's go. We had just a couple of slides left from chapter 1. I want to try to cover that quickly. Okay. Finished on this. Yep. So we're talking about sources kind of define, if it's a voltage source, it would define the voltage at cross-set regardless of the amount of current flowing through it, and how a current source would have a specific current flowing through it regardless of the voltage. Another definition here, sorry, because we changed the laptop, so here, dependent source. Now that's new, some dependent. But that specified voltage in my voltage source can be kind of controlled. Polarity plus or minus, it's still a voltage source, but in this called a controlled voltage source. An arrow showing you the flow of current, the direction of flow of current in a controlled current source. Now, so this is this one, dependent voltage source and dependent current source. How are these sources controlled? I said they're kind of controlled remotely through some other parameter existing in the circuit. And we have several types of these parameters that can control our sources. So Here we have 4 different types of dependent sources. You can have what we call a voltage-controlled voltage source. So it's still a voltage source, but the voltage of that voltage source is controlled remotely by some voltage somewhere else. It's called a voltage-controlled voltage source. And you can also have a current-controlled voltage source. So this is still a voltage source, but the amount of voltage that it has, or that it kind of maintains across its terminals, is controlled remotely by a current somewhere else. And then you also have the same for current sources. You have a voltage-controlled current source, which is a current source, so it produces a current, and the current is specified by something that controls it remotely. So you have a voltage-controlled current source or a current-controlled current source. So you actually have 4 types. You have an example here, and in this example, you have several elements. On the left-hand side, you have this plus or minus 5 volts. Now, that this is an independent DC voltage source. Okay, no confusion about this one. On the right side, you have a dependent source. So what kind of source is that? It has like 10I next to it. What is that? Yes. Exactly. So first, it's a voltage source. You know it's a voltage source because it has a polarity, plus or minus. Okay. So it means it's going to maintain a specified voltage across these 2 nodes, these 2 terminals. How much is this voltage? It is not an independent value. It's a remotely controlled value. In this case, it's 10I. And I has to be given somewhere. See this I in the middle branch? So whenever you have a current I here, your voltage source is going to be 10 times the value of this current I. It's like this current I is kind of controlling the value of your voltage remotely. Okay. So this one is a current-controlled voltage source. So this is an example, and this is the last slide for chapter 1. Calculate the power supplied or absorbed by each element in the figure. So the difference now from what we did before is that now we have a controlled source somewhere in that circuit. So let's see. I have here an independent voltage source, 20 volts, some element, another element like that, and 0.2 I. Now, what kind of element is this one? The one here. Is this a voltage source or a current source? It's a current source. Okay, from the arrow, you know it's a current source, and you have the direction of flow of the current. But this value of current is not independently specified. It's not an independent current source. The current source where the current is equal to 0.2 I, and I has to be given somewhere. So I is given here. They even tell you what is the value of I. It's 5 amps. Okay. So from that, you would know that this one here, how much is it? This is 5 amps. This is 0.2 I. So the current source here has a value of 1 amp. Okay. So what else do we have? We have a current flowing vertically here of 6 amps. I have a voltage difference between this node and this node of 8 volts. And we want to find the power everywhere. Oh, we also have 12 volts here. Across like that, that's 12 volts. Okay. So to have the power, you need, this one is element 1. So P1 here, P2, P4. So for each one, P1 is equal to V1 times I1, right? It's the product of the voltage times the current. So what is V1? That's the voltage across from the first element. So the voltage across from first element, which is V1, that is produced by the voltage source. This is 20 volts. This is what the voltage source does. It maintains the voltage across its terminals according to the value that is specified. So V1 is 20 volts times how much current do I have in here? Now, again, as I said, current is a flow of charges, and a flow, think like the flow of current in a pipe. So if I have 5 amps here in this element, it means it has to have gone this way, right? Because this current has to flow from here into there. So this one and that one, it's exactly the same current. This is also 5 amps. So I have here 5 amps. And I can get the current. But now, I did that just by multiplying V times I. Did anybody notice anything about the sign of this? Remember when we discussed the passive sign convention? Let's see. Is this current and this voltage, is it according to the passive sign convention or not? It's not, right? So it means that I have to change that into current here and call this one I1. So what's the relation between I1 and my 5 amps? It's a negative. There's a negative sign here, right? Okay. So the power here is going to be equal to negative 100 watts. So it means I have 100 watts supplied. Well, this is a source. So it makes sense. Okay. What about P? It's 5 amps. So that's plus 12 watts. I have 12 watts consumed. What do I say? Yes, 12 times 5. Sorry. 60. 60 watts consumed. Okay. P3. Look at that. You have 8 volts and the current 6 amps flowing according to the passive sign convention. So I can do that right away. P3 is V3 times I3. That is equal to 8 volts times 6 amps equals 48 watts. So here we have 48 watts consumed. Let's look at P4 now. Okay, so we have a current. How much is the voltage across this fourth element, across the current source? Yes, 8. How do you get that? Exactly. So this voltage here is known to be 8 volts. Now this node and all of that is like, there's nothing in here. This is the same. Energy level. Okay, so we're going to see that when you have several different nodes there, it means this whole line, it's really one and the same energy level. So it means that the voltage between these two nodes, that's 8 volts. It comes from here because we were given that this one is 8 volts. Okay, so how about the current? Is it in the passive sign according to passive sign convention or not? I'm supposed to say this is my current I4, right? So P4 is V4 times I4. V4 is 8 volts, but I4 is the opposite of that. There's a difference in direction, right? So I4 is not 1 amp, I4 is negative 1 amp. That's equal to negative 8 watts. Means I have 8 watts of supplied power. Okay. Now look at these numbers. Yes. Why do you say that?
Because it all sums up to 0.
Absolutely. Okay. Let's look at the amount of power supplied. This one and this one, they add up to 108 watts, right? And look at how much power consumed you have. This one and this one. They also sum up to 108 watts. Okay? And that's the balance of power that we discussed last time. So far? Okay, thank you. I'm moving on to a new chapter. Okay. So this is chapter 2, basic laws. And basically, there are 3 very important laws that we're going to be studying. You have a question?
Yeah, sorry, how did you get 1 for I?
1 for I4. Well, it's this one, right? It's 0.2 I, and I is given here. All right? So I is 5 amps. This is 0.2 I, so that's 1 amp. And the direction is vertical going up, but I want I4 to be this one, so I have to use a negative one. Yes?
So currents in parallel don't necessarily have to be the same then?
No.
If that's 6 amps.
We're going to see that. Currents in parallel, no, currents in parallel have nothing to do with each other. Voltages in parallel have to correlate, so it's because, the voltage across this element and the voltage across this element are the same because they're connected between the same 2 energy levels. Okay, so they have the same voltage across them, but the currents are totally different, have nothing to do with each other. Okay. And we're going to see that here. And this is what we're going to see now with the basic laws. So all of circuit theory is built primarily on these 3 basic laws: Ohm's law, KCL, and KVL. Can anybody tell me what is Ohm's law? Anybody else? Yes. What is V? What is I? What is R? The voltage is directly proportional to the current. Where? Not any element, no. It doesn't work for any element. You want to give it a try?
I'm not quite sure.
Absolutely, exactly. Okay, so V equals IR. This is exactly, that's what it is. So it's a definition of a resistance. The resistance R of an element denotes its ability to resist the flow of electric current. It is measured in ohms. That's the physical meaning of what it is to have a resistance. Okay, this particular element called the resistance is going to something that is impeding the flow of current. We say the element use model this behavior of the resistor. The resistor models this behavior, okay, of having this resistance happening inside. So the element is called the resistor, and it has a parameter, and moving electrons are being resisted by the atomic structure of the materials to which they are moving. So that's really what happens. And causes some energy to be dissipated in the form of heat. So if you have a resistance and you have your electric charges going through your electrons, and they're electrons, you kind of like, bumping around, like, hitting all those other atoms in there. And because of that, there's going to be friction, a lot of heat dissipate, a lot of energy is going to be going. We can compute the value of the resistance R. That's all. Are made like tiny. Now the material that is used to make this element resistance. That's the first thing. So it's proportional to the lab. Like the elements are very small, on which the current is flowing. A, it means a lot of so Ohm's law. Ohm is an individual. So I said V is proportional to I. But which V and which I and across which element? Flowing through that same resistor, and R equals V over I. R in ohms. So that's the very important foundation. Basically, Let's see, look. Fine. So what is conductance? Conductance is the ability of a material to conduct the current, which is the opposite of the ability of the material to resist the current, right? So basically, it's 1 over resistance. That's what it is. It's not more than that. The conductance, we give it the symbol G. G equals 1 over R. So if you look at your values V equals IR, it means I equals VG. Okay? V equals IR, and R equals 1 over G. So that tells me that V equals I over G, or I equals VG. Okay? So if you have an 8 ohm resistance, somebody can say, oh, so how much conductance is that? Say 8 ohms is equivalent to 0.125 moles. Okay? Now, in the Système International, they chose to use a different symbol, and they adopted the capital S, which is Siemens. So you're going to find it more common. So that's why I use the capital S instead of using the mole or the inverted ohm symbol on its head. Okay, so that's what a conductance is. Okay, I'm going to look at something that I call the limiting cases of resistances. First, we're going to define a short circuit. A short circuit is a circuit element with resistance approaching 0. That's what a short circuit is. Now, if you look at that, you don't see an element at all, right? There's nothing there. It's just a wire. So it's almost as if you're saying, oh, yes, you're right. There's nothing here. But it's like there is an element, which is a resistor, but the active resistance is 0 ohm. The current can flow through it with no resistance whatsoever. So that's a limiting case, because resistances, they tend to have a value. If you have a limiting case, or the resistance is so small that this resistance is actually 0 ohm, then your element does not resist the flow of current. And we say you have what we call a short circuit. So a short circuit is just, it's not really going to show on your drawing. It's going to be a wire, it's going to be a line. And as I mentioned just a few minutes ago, if you have a wire or a line and there is no element in there, then it's all at the same energy level, right? It's all at the same potential. This is what I have here. That's why I'm saying V equals 0. Which V? Is there a voltage difference across these 2 points? No. Those 2 points, those 2 nodes, those 2 terminals are at the same energy level, the same voltage level. That's why I say V is 0. It's like you have a virtual element that has a resistance of 0, and the voltage across it is 0. Okay. So that's what it is. That's what a short circuit is. Now, you can have current flowing through a short circuit. Yes, absolutely. You have a current that can flow. It can have any value. It may have a value, even when the voltage is 0. How can I reconcile that with Ohm's law? I mean, if I say this is a resistance of 0, okay, let's just, for the sake of argument, do that. Okay, let's say R equals, that is equivalent to having nothing like that. But if I look at it and let's see if Ohm's law is going to work, okay? Can I have the current I equals, say, 5 amps flowing? How much would the voltage be? According to Ohm's law. Zero, right? V equals, okay? You have your currents flowing through the wire. You have the current current flowing. Think in your mind, it's like a resistance. So now the other limit, the resistance is so high that the current is unable to flow. Not flow through resistance. Okay. Now resistance is infinity. How much can you have a voltage across these two? Across these two nodes? Could you have a voltage here? Yes, you can. The voltage can take on any value, and the current is going to be zero. Because if you look at Ohm's law, let me put this one here. We call that an open circuit, OC, like that. Okay. So this is equivalent to a resistance that tends to infinity. And if you have a voltage here, V, I equals V over R, right? And I want to know how much current there is. Let's say V can take any value, okay, 10 volts. How much is the current I? It's going to be 10 over infinity. How much is that? When you divide a number by infinity, what do you get? 0. Okay. So these two limiting cases, what do they tell us? They tell us that when you have a short circuit, and I'm going to call this one short circuit, you can call it like that, like SC. This one is open circuit, OC. In a short circuit, you can have a current flowing and 0 volts across the ends of your short circuit. When you have an open circuit, you have a voltage, but 0 current flowing through it. These are the limiting cases. And they can still relate to Ohm's law. Okay. Okay. Power in a resistor. Now, any element, we know that the power is the product of the voltage across it multiplied by the current flowing through it. Okay. Look at that. In a resistor equals V times I. But we know from Ohm's law, the resistor is related to the current flowing through it by Ohm's law, so V is equal to IR. If I substitute here, it's going to be equal to IR times I, which is I squared R. Okay? And that's the equation of the power in the resistor, I squared R. So please never try to compute the power using I squared R in any element except a resistor. Because see, we inserted Ohm's law in here. And Ohm's law pertains only to resistors, right? So if you want to use the general equation P equals V times I, like we used it in the example I did just a few minutes ago or last time, that's the generic formula, P equals V times I. But if you have a resistor, you know the value of the resistor, you know the current flowing through it, instead of trying to figure out how much voltage and then multiplying the voltage times the current, you could kind of go through a shortcut and say the power in the resistor is I squared R. We can also use this other substitution in here, because we could also say P equals VI, and I'm going to leave the V and replace the I by V over R, so I end up having V squared over R. They're the same. It should give you the exact same value of power. So there you go. You have the power equals VI, that's the generic formula. In a resistor, you could use I squared R or V squared over R. V, in this case, obviously, is the voltage across from that particular resistor. Okay? So because the power is equal to I squared R, even if I is negative, you end up getting a negative power consumption. It's always going to be positive, right? Because it's I squared. And because it's V squared over R, even if V is negative, you end up having V squared over R as a positive value. So in a resistance, the current and the voltage will always work out to give you power consumed. You can never, ever have power generated or supplied by a resistor. Okay? Again, and I'm going to put that here. to be clear on that. If I have a resistance, R, because we know from these formulas that V equals I squared, power is equal to I squared R, or V squared over R. So it's going to always end up being power consumed. It tells us that the voltage and the current in a resistor are always according to the passive sign convention. Okay? The real value of the voltage and the real value of the current, if you measure them in a lab, you will always find the current inside the resistor flowing from the higher voltage to the lower voltage. It will always have to be this way. Because, remember we said this is the passive sign convention? Passive sign convention means it relates to passive elements, and the resistor is the, passive elements like by default. That's the main passive element that we have. So voltage and current are always going to be inside the resistor or across the resistor according to the passive sign convention. You can never ever have a current flowing inside the resistor from the lower voltage level to a higher voltage level, and it's not physically possible. Now, if you have a source, it is possible. Okay, so a source can give you power, power as well, a source as well. I mean, remember the example of the car battery? They have two sources, but one of them was giving energy to the other one. So a power source can also receive, so it can be on the receiving end. A power source may end up eventually giving energy to the circuit, giving power to the circuit, or maybe it's placed in such a way that the power is actually going inside the battery, like charging a battery. You know how you charge a battery. So if you have a source, you can never tell before you solve your problem if the power is going to be, supplied or consumed. But what you can always be sure of is that in a resistor, the power is always going to be consumed. Okay? Example. An electric iron draws 2 amps at 120 volts. Find its resistance. Simple. Can somebody tell me how you do that? What's the resistance here? According to Ohm's law, what's the resistance? Yeah, what's the formula? V over I, right? So this is Ohm's law rewritten. And the voltage is 120 volts, current is 2 amps, so you get 60 ohm. Okay, thank you. Another example, in the circuit shown, calculate the current I, the conductance G, and the power P. Okay, look at that. I have a voltage source here of 30 volts. A resistor of having a resistance of 5 kilo ohm, and we want the current. What do we want? We want the current I, the conductance G, and the power P. So look at that. I have a source of 30 volts. This is a voltage source. It's going to maintain a potential difference between its two terminals of exactly 30 volts. Now, as I showed you before, this and that, there's no voltage here, right? This is short circuit, if you will. This is just one short connection. There's no drop here. So the voltage or the potential at this node is equal to the same as that. The potential at this node is at the same energy level as that. Those voltages are energy levels, remember? So I know that the voltage across of my resistance between here and here is also 30 volts. So let's look at this now. V equals 30 volts. R equals 5 kilo ohm. I, according to Ohm's law, is V over R. equals 30 over what? Over 5? Over 5K, over 5,000. Let's see. If I do that, 30 divided by 5, that's 6. But 6, if I'm going to do that. Look. When this one is in kilo ohms, so this one is 6 over 1,000, right? So 6 milliamps. Here, okay? Because it's 6 times 10 to the negative 3 squared times r. What's r? 5K. That's 5 times 10 to the positive 3. So what do you get? That's 36 times 5 times 10 to the negative 3. Okay? That's equal to 180 milliwatts. I did that using I squared r. Let's do it using V 10 to the negative 3. So that is 180 milliwatts. Okay, same thing. And I'm going to do it a third time using the original equation for power, which is V times I. So it's 30 times current I. We found it to be 6 milliamps. So it's 180 milliwatts. Okay, so you could use whichever you're more comfortable with. Another example, a voltage source of 20 sine pi t volts is connected across a 5 kilo ohm resistor. Find the current through the resistor and the power dissipated. Okay. A voltage source is connected across a 5 kilo ohm resistor. So again, we have a 5 kilo ohm resistor, and you have a voltage source that maintains the voltage across it, which is 20 sine pi t volts. We want to find the sine pi t over 5k, which is 4 sine pi t, but because of the k, I get a milli here, so it's milliamps. Okay. Whatever, V times I squared r, V squared over r. I squared r equals this one squared, that's the current, so it's 16 sine squared pi t, but be careful, because of the milli here, you get times 10 to the negative 6, right? Times 10 to the negative 3 squared. And I have to multiply that by r, which is 5k, times 10 to the positive 3. So I end up having 80 sine squared pi t times 10 to the negative 3 here, which is a milliwatt. Okay, any questions? So this is Ohm's law. Ohm's law is very good at helping us model different things in nature. So I mentioned that last time, when you have a resistance in the circuit, it can be the model for a lamp, for example. Okay, if you have an electric circuit and you want to show a lamp in that electric circuit, you're going to model the lamp by a resistor, because in fact, this is what a lamp does. It takes energy out of the circuit and it dissipates it in the form of light, and there's a byproduct of heat as well, so it's light and heat together. So this is what a resistance can do in an electric circuit. It can model, other phenomena that would behave like passive elements that consume energy. So in here, we're modeling a human body with resistances. Okay? Because if there is electricity going through your body is going to resist that. Okay, so there is resistance in there. And if you have this particular person standing, we're going to model the different parts of their body with different resistances. The reason we're doing that is because we want to know how much resistance is in your body. If there is a voltage applied across from your hand to your foot, okay, like that. Actually, see that voltage V? You may have a current flowing through resistance RA, RT, and RL. So which is like your arm, your trunk, and your leg. Current's going to flow through these three together. And look at that. This is the reaction to what would happen if current flowed through you. So if the current is between 3 and 5 milliamps, it's very perceptible. You may not even be aware of that. And that's the level of current that you have in microchips. That's the level of current that you have inside the computer chip. That's just a few milliamps, sometimes even less than that. So this is kind of safe, right? We don't have an issue carrying our cell phones in our pockets. We know nothing's going to happen to us. If you go from that to just 35 to 50 milliamps, then it's already extreme pain. Okay, you reach that very, very, very quickly. And then, if it goes beyond that, from 50 to 70 milliamps, you can experience muscle paralysis, and your heart is a muscle, remember that. Further, maybe your heart can take more than that. So obviously the heart can take all the way up to 500 milliamps, which is half an amp, okay, current. So when we're talking about, I have in my circuit 10 amps and 15 amps and 25 amps and stuff, this is no joke, okay? Well, obviously, that current is not going to be able to flow through your body because there is a lot of resistance in your body. Remember, if there's a voltage across a resistance, Ohm's law tells us that the current is V over R. So if there's a lot of resistance, the current's going to be small. So for a current to reach these levels in your body, it means that the voltage has to be very, 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 very high. And that's why you have like some panels sometimes in places in electrical rooms which have this warning, okay, high voltage. Because if it's a high voltage and you go in there, and this voltage gets applied across your body, then the current flowing can potentially be high and it can harm. We're going to move into something a little bit different here. We're going to look at the topology of electric circuits. We're going to define branches and nodes and things like that. So a branch represents a single element, such as a voltage source or resistance. That's the definition of a branch. So if you look at a circuit like that, you have 1, 2, 3, 4, 5 branches, right? Each branch is the representation of one of the elements that we have studied so far. Now look at the circuit that is drawn to the left-hand side, where everything is just nice and neat in parallel and perpendicular lines. This is the usual way to draw the elements that are connected together in electric circuit. This is how we tend to like to draw them, okay? But there is absolutely no problem drawing it like it is on the right. Okay, in this case, it kind of looks more curvy, but it's still the same circuit. It represents the same interactions between the different elements in your circuit. And we're going to see that when we define what a node is, because a node is the point of connection between two or more branches. So if you look at that, if I compare those two diagrams, look at node B on the left and node B on the right. On the left, it's almost like you have three separate nodes, right? In that nice and neat circuit. But in fact, those three nodes, they don't have any elements in between, right? So we don't really acknowledge them as being separate. We say it's like the three nodes are really one node. And like I said earlier when I was doing some solving a problem here, a node is usually at a given voltage level, at a given energy level. And if two nodes are shorted together, they have a short circuit, like there's no element in between them, it means that both of them are at that same energy level. So you might as well draw them as a unique single node. So that's why I could, instead of drawing it like it is on the left here, with the three red dots representing, you know, as if they were three different nodes, I could still draw it this way, but in my head, I have to remember that it actually kind of behaves like it's on the right. It's really one node there. Same thing for node C in the bottom. See all those in the bottom over there, down there? They're all at the same energy level, same voltage level. And they all are basically like one single node. A loop is defined as any closed path in a circuit. Because we're going to be going around loops. So any closed path that qualifies to be called a loop. Okay. Now there is a theorem here. It says that if you have a network with B branches, the number of branches is B, N nodes, and I independent loops, it would satisfy the fundamental theorem of network topology, which states that the number of branches B is equal to L plus N minus 1. Okay. And when I say L independent loops, I want to explain what that means. Look at this circuit. How many loops can you find? So a loop is you start from any point and you go around any path and you end up at the same point again. It's any closed loop, yes, any closed path. 3. But these are the inner ones, right? They have 3 inner loops. These inner loops, we call them meshes. We're going to get to that later. So we have 3 inner ones. But do you find more loops? Yes. Which one is the fourth? The entire one. Okay, but there are more loops. Yes. You got 7. Maybe yes. So how many loops? I mean, because you can go around the first mesh, the first inner one, the second inner one, the third inner one. Then you can go around the first, two, like the first and the second one together, around them, right? This is still a loop. It's called a loop, okay? And then the second and the third one, you can go around them together. And then you can go around the big one. I don't know where's the 7th.
Oh, no, I guess.
Yeah, so you do have 6, but they're not 6 independent loops. Fine. If you can make out of other loops that you have already counted, then they're not independent. But what I mean by that, the outer loop is not independent because we've already counted the 3 inner ones. Okay? So the big one is made of those 3. So it's not independent of those 3. So the theorem here is talking about independent loops. How many independent loops do I have? Well, we have the 3 inner ones. These are independent. And then, let's see. If I make up one loop made of loop 1 and 2 together, we counted this one as a loop, right? But is it an independent loop? It's not an independent loop anymore because we already counted the 3 inner ones. Okay, what about the loop made from loop? It is a loop, but it's not an independent loop. And if I count the outer one, it is still a loop, but it is not an independent loop because it is made of those 3 inner ones. So basically, independent loops, the number of them is equal to the number of meshes, the number of the inner loops. Okay? So that's L in this circuit. L is equal to 3. How many nodes do you have? How many nodes do you see? Yes, exactly. You have 3 nodes. Okay? You see that? You have nodes A, B, and C. So A is a simple node, just the node between those 2 elements. And then B is this node that is but we can group them all into one node, and same for C. So what is the number of branches B? B is equal to L, we counted 3 independent loops, plus N, we counted 3 nodes, that's 6, minus 1, so that's 5. So do I have 5 branches in the circuit? Yes, I do. Okay, so this is just a network theorem that kind of lets me know that I counted my branches right, my nodes right, and my loops right. Okay. This is the definition of elements in series. And you notice that I crossed out something. That's the definition that's in the book. The book says 2 or more elements are in series if they exclusively share a single node and consequently carry the same current. I beg to differ. This definition is not accurate. It would be accurate if you strike out that, like this or more part. And I'm going to explain here what I mean by that. If I have 2 elements like this, and let's read the definition. 2 elements are in series if they exclusively share a single node. Now, do they share a node? These here. Yes. Okay, this node in between is shared between these 2 elements. Do they share it exclusively, meaning that there is no other element, that is coming there? Okay, yes, they share it exclusively. Okay, so do they carry the same current? Well, let's see. If you have a current flowing in this direction, I1, and a current flowing in this direction, would it be the same current? Yes, it would. Remember, current is a flow of charges. If it flows through this element, it has nowhere to go. It has to flow. In the other element as well. Okay, so now these 2 elements are instead, they share exclusively one node. So this is current I1, this is current I1, this is current I1. Yay, they're in series. Okay, that obviously doesn't apply. So this equation, this definition would work if you remove those 4 more elements. Now, when we have more than 2 elements in series, it would look like this. Now, these 3 are in series now, but the sharing of nodes happens exclusively only between every 2. So these 2 share exclusively this node, and the second and the third one, they're going to share exclusively another node. Okay, and the current I1 is going to be the same as here. It's going to be the same as here. Yes, this is in series. Okay, so these are elements in series. So think of a train. Okay, a train is made of several cars. And this is how elements in series look like. Okay, one pulling another car. Is it possible for that cars move at different speeds? No, it's all moving together, right? It's like that's the same thing here when you have current flowing through elements in series. Okay, imagine like these are like they have to be connected like that. This is what makes them in series. Okay. Now, when they are in parallel, we say 2 or more elements are in parallel. And here I'm okay with the or more part of the definition because it works for parallel. I don't have an issue here. So 2 or more elements are in parallel if they are connected to the same 2 nodes and consequently have the same voltage across them. This is the definition of elements in parallel. So let's see. I'm going to draw elements in parallel here. If I have two elements connected across the same 2 nodes. You know, they share those 2 nodes at the 2 ends of my element. Okay. If you have a voltage difference or a voltage drop or a potential difference across from these 2 nodes, it would apply to both elements. It would be the same. So if you have a voltage V1 across the first element, it's exactly the same voltage V1 across the second element. And that's what it means that they are in parallel. Now, can I have more than 2 elements that have this, like this characteristic? Let's say I'm going to connect another one like that. This third element is in parallel with the first 2. No issues here. Okay? And more. You can put as many as you want. Okay? Now, often we don't draw it like that. You're going to find a drawing that looks more like this. Okay? Same thing. We already discussed the fact that all of that is one node, and all of that is another node, which means that my elements are all connected between the same 2 nodes, and consequently, they share the same voltage across them all. What about the current? Did we discuss the current? Is there any relation between the current here and here and here and here? No. Those currents, you know, they can take on totally different values. And if we go back to our series connections up here, I said this current is the same as this one, is the same as that one. What about the voltage drops across them? I have a voltage here, V1, a voltage between here and there, V2, a voltage between here and there, V3. They can be totally different from one another. Okay? So that's what you have to keep in mind. Elements in series, they look like this, and they share the same current. Elements in parallel, they look like that, and they share the same voltage or potential difference. Let's look at those circuits on the board here, on the graph. Can you find 2 elements in series? Can anybody find 2 elements in series? Yes. Which resistor?
The 5 ohm one.
Exactly. The voltage source, the 10 volts, and the 5 ohm resistor. Okay, they are in series. All right? So it doesn't really matter if they are drawn perpendicular to one another. I mean, that's not the issue. That's a matter of just the style of drawing. But the current doesn't see that. The current leaves the voltage source, goes into the resistance. They share one node exclusively. Okay, they are in series. So can anybody see elements which are in parallel? The 2 ohm and the 3 ohm resistor, they're definitely in parallel, but there is something more. And the 2 amp current source, those 3 branch parallel. The 10 volt in parallel with the 2 ohm resistor. Why not? Exactly, they are not connected between the same 2 nodes, right? There's another element, this 5 ohm there that exists, okay? So I notice that sometimes people can get confused because they look parallel, meaning parallel in a geometric sense, right? They're both vertical like that, and so I think, oh, they are in parallel, but they're not. Electrically speaking, you have to be careful. Determine the number of branches and nodes in the circuit shown. Identify which elements are in series and which are in parallel. So what do we have here? How many branches do we have? You just count them. We said a branch contains an element. So how many branches do you have? How many? Let's start with the nodes. How many nodes do we have? This is one node here, right? These together form one node. That's node 2. And all of that is one node. Okay, 3 nodes. So n equals 3. How many loops do I have? Independent loops. The easiest way to count the independent loops is to look at the inner loops, the meshes. So I have 2. B equals n plus L minus 1. That's equal to 3 plus 2 minus 1. That's equal to 4. Do I have 4 branches? Yeah. 1 branch, 2 branches, 3 branches, 4 branches. Okay, and here it is. Okay, let's go into Kirchhoff's law. Do you know about Kirchhoff's current law and Kirchhoff's voltage law? I think I asked this question last time. So we're going to start with Kirchhoff's current law, or we call it KCL. KCL states that the algebraic sum of currents entering a node, between brackets here it says or a closed boundary. I'm going to leave this part for later, the closed boundary point. But for now, we're going to think about it as currents, the sum of currents entering a node is 0. When they say the algebraic sum means you have to take the sign of the current into consideration. It can be positive or negative. Okay? So what does it mean? It means that if you had something like that, So we're going to assume all of them entering the node with different signs. Okay. So if I have that, I have here a current I1 entering the node. The current I2 is actually leaving the node, right? Current I3 is entering. I4 is entering. And I5 is leaving the node. So Kirchhoff's current law would say that I1 minus I2 plus I3 plus I4 minus I5 equals 0. Or, I like to say it in a slightly different way. I would say the sum of the currents entering a node is equal to the sum of the currents leaving the node. So let's see here. How many currents entering the node do I have? I have I1 plus I3 plus I4. That has to be equal to the sum of the currents leaving the node, which is I2 plus I. Okay. So these two equations mathematically are exactly the same. So some people prefer to look at all the nodes as if they're entering, and you change the signs, and you say the sum of all of these currents is equal to 0. I find that this is more intuitive. Sum of the currents entering a node is equal to the sum of the currents leaving the node. Why is that? Now, remember the current is really like a flow. Think of the current of water. If you have flow I1 and flow I2, flowing like that into a node, what comes out in the other side here has to be the sum of these two, right? That makes sense. So this has to be I1 plus I2. Okay? Now, if you have more than one current going out, let's say you have something like that. So all of these that are entering, the sum of all of these has to be equal to whatever is going out of them. Okay? So it's just KCL is intuitive, KCL is easy, it makes sense. And these are the two ways to write that. So the sum of the currents leaving the node, and that's the other way that I personally prefer to write. I find it easier to write. Okay. Stopping here. Thank you very much.